Everybody's sleeping. It's gonna be our holiday card, maybe. That is really, really funny that the dog's just like, I know, right?
All right, so I think we have a good shot at finishing homework number 6 material today, which means that you guys will have all of that in hand when I assign it. That won't be due until the week after the exam, so your first exam is what, 1 week from today? Did I have that correct this time? So we'll do new material today and Tuesday, and then you will have that homework. I know that the very first thing after you take the exam will probably be to run and go home and start homework 6, so it'll be ready and available for you whenever you want to start that. Okay, any quick administrative or logistical questions before we get started? Okay, so let me remind you about the theory for circular motion, and then we'll do a couple more examples. So going in a circle is a privilege, not a right. There's a certain force requirement that you must have. In order to go in a circle, the amount of force needed is called the centripetal force. And the amount of force, there's not a one-size-fits-all amount like 5 newtons. It depends on the mass of the object, its speed, and the radius of the circle you want to take it in. That's how you figure out how much force is required to hold a particular circle. That force is radially inward. You're basically hugging the turn, keeping it constantly around a common center. Just because you want to go in a circle doesn't mean you get to. One or more actual forces must supply the amount of required force. Candidates might include tension, normal force, gravity, friction, maybe some combination. Those have to step up and meet this requirement. If they don't, well, you just don't get to go in a circle. If you don't exert enough force toward the center, if the actual force is smaller than the requirement, you'll fly out. The extreme case of that is you don't exert any actual force at all. Then you won't maintain a circle. You'll just go out in a straight line, certainly flying out from a circle. So what happens if you get pull too hard toward the center is it actually will go into the center. So you'll collapse the circle. That's when the actual radially inward forces exceed the amount required to hold the turn. It's only if you manage to pull toward the center exactly the right amount that's required will you maintain your circular motion. So what I want to take a look at next is an example, a quantitative example, where I have multiple forces that are part of the team that is meeting the requirement. Here's my example. I have a road, and that road is going to have a bump. I'll have a car driving along this road. Let me have that the speed of the car is 10 meters per second. Let me have the mass of the car be 100 kilograms. That, by the way, is a very small car, okay? It's like 200 pounds, but I don't want the numbers to get too unwieldy, so this is like a go-kart or something, I guess. Let me also say that we have a car on cruise control. So cruise control is, of course, your way of telling the car to maintain the speed. And so if point A is a flat ground, point B is going to be the top of this bump. And we can count on it not having slowed down as it goes up to the top of a bump. So the engine has somehow compensated for that. Of course, normally when you go uphill, you slow down. And then finally, let me give some structure to this bump. The structure of the bump, it'll be a part of a circle of radius 20 meters. So here's my question. At both of these points, I want to know the support force from the ground. So let's start at point A. How many vertical forces act at point A? Two. Force of gravity pulls down, and the normal force acts up, and they cancel. And this thing is able to maintain, by Newton's first law, constant velocity, right? Constant speed in a straight line because these two forces cancel. So here's what it looks like. At point A, just to belabor the obvious, let me set plus y direction to be upward. F net y equals ma(y). We have normal force acts up, gravity acts down, and there is no y acceleration. And we get a perhaps rigorous proof of the obvious. Hopefully at this stage you can already see that the normal force and mg are the same size, and if you multiply the numbers you'll get 980. Okay, that's old news. That's just setting a baseline for, of course, where the action is in this problem, which is at point B. So let's move to point B. How many vertical forces act on point B at, on the car?
2.
0? Anybody? Raise your hand if you think there's 1. How about 2? How about 3? Okay, most people said 2. That's right. Same 2 as before. Force of gravity acts down, and normal force acts up. Common misconception is that there are 3, normal force, gravity, and centripetal. But that is thinking of centripetal as some kind of completely independent phenomenon. There are no magic elves that come and act on things only when they're going in circles, okay? There are 2 forces, same as before. Centripetal force is requirement. When you're going in a circle, your net force is not 0. And I would point out that if these 2 forces cancel, you'd have to do the same thing you did over here, which was go in a straight line. But you don't. You curve down. So, if you're going to curve down, then you need the down force to win. In fact, we've already learned that when you go in a circle, the net force has to be toward the center. So, in this case, that the center of the circle is below. So you need a net force downward, which means the down force is bigger than the up force. Let's write down the equation. We can start at the same place, F net y equals ma(y). The forces are normal force acts up, gravity acts down, but now this side, other side is not 0. You are accelerating. You are accelerating toward the center of the circle, We call that centripetal acceleration. We call m times a, we call this the centripetal force. So this is just a statement of the actual forces that are acting must meet the requirement. So we go ahead, we say the force is of size mv squared over r, and then of course toward the center of the circle now must be encoded by minus. So remember, over here, don't forget about the direction. Radially inward, you may occasionally need to use a sign to code that in. So the way to think about this is you have two actual forces, one acting up, away from the center of the circle. We have gravity, which is acting downward toward the center of the circle. And we overall need a force toward the center of the circle. Okay? So we can solve here. The expression would be mg minus mv squared over r. And I can tell you the number. I'll tell you that in just a second. But I do want to point out that you should already be expecting that the normal force is less than the force of gravity. You can certainly see the structure of it from the solution. N is not mg, N is mg minus some crap, right? So N is going to be smaller. Or you can think of it conceptually. You need a net force toward the center of the circle. In that case, that's down, so the down force must win. Mg must be bigger than N. Let me even, to drive this point home, put in the numbers. I have m, v, and r. So I know what it costs to take this mass at this speed in this circle. If you work out that number, you should find that you need 500 newtons toward the center. 500 newtons is what is needed toward the center to maintain this mass at this speed and this radius of a circle. Now if you work out the other numbers, gravity is 980 toward the center. Too much. If you only needed 500 newtons toward the center and you had 980 toward the center, what would happen? What would happen to the circle?
Collapse.
It would collapse, right? It would be one of these things. The actual amount of force you have toward the center is 980. You only need 500. And if the road weren't there, that's what would happen. The car would fall in. But this is an empty space. There's a surface there that says, hey, wait a minute. Can't come in here. Okay? There's a road here. Solid surface must be, it's a forbidden zone. So that's where the normal force kicks in. But notice, it does not have a problem with the first 500 newtons acting toward the center. Because the first 500 newtons is no threat to the surface. The first 500 just makes sure that you don't go straight, you do this, you curve, right? But there's no danger of smushing the road, you're just following the road. The problem that the normal force had is with the gravities being more than that, right? Being too much. So it balances the load out. It's 480 newtons upward. It just cancels off the overage. Out of that 980 newtons total of force of gravity that's acting downward, the first 500 don't threaten the structural integrity of the surface at all. It just keeps the thing going along the surface instead of flying away in a straight line. It's the 480 newtons too much, and that's what the normal force cancels. Remember, the normal force always protects the structural integrity of the surface, and in this case, it needs to exert only 480 newtons to do that. Okay? So, the force of gravity is 980, but the normal force is only 480. The difference between the two is what maintains the circle. Okay? So, putting it over here, normal force is 480. Okay. So, we learned that the normal force has a special place in terms of apparent weight as well. How heavy you feel is based on the normal force. So when you're going over a bump, you will feel lighter than you do normally. Has anyone ever gone over a bump and experienced this? Felt lighter? Maybe even feel like you lift out of your seat. The reason why is that the ground doesn't have to push up on you as hard as it normally does. If you're going in a circle, part of the force downward by the force of gravity is just maintaining the circle. It's only whatever's too much, if anything, that is the normal force's job to cancel. So you will feel lighter when you go over a bump. Another homework problem that you have at some point thrown in, what happens if you go on a dip? So you go like this instead. You go like this with the center of the circle being above you instead of below you. So it's another thing you can probably figure out. You feel heavier. If you've ever gone on a dip, you feel heavier. Okay. Now, obviously, the apparent weight stuff will remind you quite heavily of that elevator problem, which you should, of course, know for the first exam, homework number 4. So let's compare and contrast. How is this different? So I'll put alongside here the elevator problem. Everything was the same for both of these. Both of them let's say both of them are accelerating downward and have a net force downward. So that's certainly true for the car, right? Because the center of the circle is below you. If the center of the circle is below the car, you have to have a force towards the center, so that's downward. And then let's juxtapose it with the case where you're accelerating downward in the elevator. So in the elevator, same deal. You had a force of gravity, you had a normal force, and they are again out of balance. And same deal, if you need a net force downward, the down force has to win, and the up force has to lose. So again, your apparent weight is smaller than your actual weight. You will feel lighter. So all the same things. Now, the only difference between these two scenarios is this. In the case of the elevator, you're accelerating linearly, which means that you are going to change how far you are from the bottom of the elevator shaft, right? This is a single line that you're moving on. You're going to change your distance away from the bottom of the elevator shaft. You are not changing your distance from the center of the circle. The only reason for that is that you have sideways motion at the same time, which means that as you accelerate, you don't actually get any closer to the center. That's the only practical difference, is that if you happen to have sideways motion, you can accelerate towards the center of the circle without actually getting any closer to it. That's the thing you have to wrap your head around with circular motion. You're always accelerating toward the center, but you never get any closer to it. Okay? So in linear motion, all we have here is ability to speed up and slow down. That's the only thing that can happen along a single line when you apply acceleration. But circular motion is this weird thing where you're always accelerating, but because that acceleration is applied perpendicular to your velocity, all it does is curve the motion instead of changing the speed. Okay? Are there any questions on that? Okay, so you'll definitely have several questions on your homework where you have to tally up. There may be 2 or more actual forces on the left-hand side, and that is contributing to the requirements to go in a circle, which is mv squared over r toward the center, and toward the center, again, may have to be encoded as a minus sign if you happen to choose plus to be away from the center, which I did in this case. All right? Any questions before I move on to the next example? Okay, so now let's take our ideas of circular motion and combine them with our newfound universal gravitational ideas and do orbits. Let's talk about orbits. So let me take a classic situation here. I'll take the mass of the Earth. That's the Earth. And I'll take something that is orbiting the Earth. So we know from Newton's first law that if that object up here did not have any force, it would go like this. The net force would be 0. But it doesn't fly off in a straight line. What is it that keeps it around? It's its gravitational attraction to the Earth. So it goes like this. Of course, we learned that gravity is a mutual thing. So really, the moon, the satellite here, which is going to be the moon, I'll take our oldest satellite, the moon. The moon and the Earth are attracted to each other. So why is it that the moon orbits the Earth and the Earth doesn't orbit the moon? Well, it's just the relative masses, right? So the force is a much bigger deal for the moon and a less bigger deal for the Earth. The force on the moon is what keeps it in orbit, and the effect of that same force back on the Earth, which is much more massive, is a slight little wobble. That's all. In fact, it turns out that they really both orbit a common point, but that common point is much closer to the Earth. Okay? We'll learn about something called center of mass a little bit later on. So the center of the Earth, center of mass of the Earth-Moon system is basically so close to the Earth's center that it's inside the Earth. So the Earth has a little wobble. The moon is where most of the action is. Okay? So let's calculate something about the moon. Well, the moon isn't going anywhere. So apparently the actual force and the required force are equal. The gravitational force is just right to meet the requirements to go in a circle. So that seems like lucky coincidence, but of course there were things that the actual force, or there were things where the speed wasn't correct. It was going too slow. Those are things that back in the formation of our solar system might have collapsed and joined the Earth. There were things that were moving too fast and flew away. But there were some chunks of stuff that were flying around at just the right speed to get captured in orbit. Their attraction to the Earth perfectly kept them around, circling the Earth, not flying away, not collapsing towards. Okay? So let's work out the details. We'll put in our universal gravitational law. We'll put in our centripetal force law. We have to make sure there to put in on the right-hand side. Of course, on the right-hand side, the mass that's being taken in a circle is the one you should put in. So that's why I put in the moon's mass. And this can be our platform to finding out how fast is the moon going. That might be an interesting thing to find out. How fast does the moon orbit? So let's work it out. Now, if something has more mass, the moon is quite massive, it needs more force to hold it around, right? So if the mass of the moon is bigger, the force needed to hold it is bigger. But this is the convenient thing about gravity. If you need more force, because you have more massive, you get more force. So the mass doesn't matter. So the moon could be any mass, as long as it's going the right speed, it will stick around. Let's keep going. We have two r's here. We should double check that they're the same r. R is the radius of the circle for the centripetal force formula, and it's also the center-to-center distance here, so that is the same r. You can cancel off one of those, and then I'm pretty much done. I can calculate the orbital speed of the moon. And really, of course, we said that the moon's mass canceled. So this is really a relationship for anything that you want to orbit the Earth. Okay? The only thing that enters in to the equation, well, of course, the universal gravitational constant, that's a constant. The Earth is the planet. The only thing you need to do to figure out how fast you need to orbit is where you are. And you can see that the further away you go, the slower you're allowed to go, okay, and stay in orbit. Okay, so it kind of makes sense, right? As you get further away from the Earth, the gravitational pull diminishes significantly. You can go slower without accidentally